going to use this instead. Woo. All right. Well, here we are. We are still in Lecture 7.3, and we have an example to do. So you may recall that in Lecture 7.3, we were learning about the diagonalizing basis, and the transformation that got us there was to use the Eigen vector matrix, or the modal matrix, and we found out that when we went into this diagonalizing basis for our state vector, that our A matrix, the transformed A matrix, sometimes we call it the A prime matrix, is just the eigenvalue matrix, which is the matrix, the diagonal matrix with eigenvalues along the diagonal and zeros elsewhere. So that's what we learned about, and we learned that we can use this formula here actually to compute what the state transition matrix is in the original basis using the easily found state transition matrix in the primed basis and the eigen vector solution, the modal matrices and their operation on phi prime. So this is where we were. We're going to do a little example, the state free response. So for the state equation given here, find the state's free response to initial condition to -1. So it's a 2x2 A matrix. So this is a what order system? Second order system. Very good. And we would like to find this free response given an initial condition. So, I mean, pretty nice that we can now just directly solve this, right? So let's do that. So we don't have to transform this into the input-output ODE and then go through that process. We can just apply our direct solution technique, which I think is much quicker, much more direct. So the first thing we need to compute are our eigenvalues. And as usual, we need to find the determinant of lambda I minus A and set that equal to 0, which will give us our characteristic equation and give us our eigenvalues eventually. So this yields determinants of lambda I is lambda 0, 0, lambda minus A, which is -2, 2, 2, -3. And once again, going through the steps in gruesome detail, almost, right? It's almost too much. Almost getting bored. So much detail. Lambda plus 2, -2, -2, lambda plus 3. And now we'll finally take the determinant, which gives us lambda plus 2 times lambda plus 3 minus 2 times 2 is 4 equals 0. Simplifying that into a polynomial gives us, and solving, let's just do that. Solution, we get lambda 1 and lambda 2 being equal to I actually wrote out decimals, so that's what I'm going with here. Negative 4.56 and negative 0.438. Okay. So those are the eigenvalues. They're real again, right? So we're going to do in the next lecture complex ones. So now we need to find the eigenvectors. So we find them by looking at this problem, lambda I minus a times an eigenvector is equal to 0 vector. And let's plug in, I liked what we did last time where we said, okay, let's do this for lambda I. So we already did lambda I minus a up here. So we're just going to copy that matrix down. So lambda I plus 2 minus 2 lambda I plus 3 times whatever the eigenvector is. So m1 I, m2, no vector on those m's, m1 I, m2 I, because they're inside the vector already, equals 0, 0. So let's plug in lambda 1 equals negative 4.56. And that's going to give us, I'll go ahead and plug it in the first time. Over here. So negative 4.56 plus 2, negative 2, negative 2, negative 4.56 plus 3, m1 1, m2 1 equals 0, 0. So remember, we can take either equation. They're linearly dependent equations, so it doesn't matter which equation we take. If you want to check to make sure you did things correctly, it's good to check that you have linearly dependent equations. You should, okay? Okay, so like for instance, you can take this first row, which would say negative 2.56 m11 minus 2 m21 equals 0. And then you can say let m11 equal, let's see, actually, just because my notes did this other thing, I'm going to say let m21 equal 1. And that yields, if you plug into this equation, m11 equals negative 0.781. So therefore, our eigenvector m1 is equal to any scaling of negative 0.781 and 1. Okay. Similarly, we can do that with lambda 2 equals negative 0.438 and we plug that in, and negative 0.438 plus 2, negative 2, negative 2, negative 0.438 plus 3 times M12, M22 equals 0, 0. And that yields the equation in the first row is 1.562 M12 minus 2 M22 equals 0. And if we let, for some reason I was really into letting the second one be 1. So let M22 equal 1. And we get that M12 equals 1.28. So, therefore, M2 is equal to some scaling of 1.281. And I know that you guys, with your calculators, can compute eigenvalues and eigenvectors. It's fine with me. It's possible, though, that I could give you one of these problems with symbols in them, and then your calculator can't do it.
So for M1 vector and M2 vector,
yeah.
do we have to write it in that notation, or could we write, instead of solving for the two numbers, M12 on the top and then M12 times a variable on the bottom?
No, because you have to scale the whole vector, because this ratio, the ratio between these two values has to stay the same. So that's why I mean I don't even care if you put in this scaling factor. A lot of times we just skip it when we write this, but we can't write, for instance, like this could not be beta.
But could it have beta in both of them?
Oh yeah, could it have beta in both of them? Yeah, you could put that. That would be fine. Yeah, if you wanted to, like 1.28 beta, 1 beta. I mean, it's pretty standard to just leave off the scaling factor. It's up to you. I just like to put it in there to remind us that it's really any scaling of that is valid. Great. So, we have our eigenvalues and eigenvectors. So let's form our matrices. So we have the eigenvalue matrix, which is just the eigenvalues along the row. I'm just going to write lambda 1 and lambda 2. 0, 0. And we have our modal matrix, which is just M1, M2. So I will actually write this one out because that's a little bit more confusing to look at the notation. So this one is negative 0.781, 1.281. Okay. So let's recall what the problem asked for. It said find the state's free response to this initial condition. Now, we've got a non-diagonal matrix, but the state's free response is just going to be the state transition matrix times the initial condition, right? So we just need to find the state transition matrix. So since we've got, I mean, the reason why we found the eigenvalues and eigenvectors is because we're going to find that state transition matrix. So now we're ready for the state transition matrix, which is phi of t equals m phi prime of t, inverse. So m inverse, we're going to have to compute. But this formula, let's remember where this formula came from. It's this formula, right? We just derived this. And we do need to know what phi prime is. But remember, phi prime is super easy to find. Let's go back and see if we can find it in the notes. It's just the exponentials along the diagonal of a diagonal matrix. So it's e to the lambda t. So we already have that. So we have, I'll say phi prime of t equals e to the lambda t equals e to the lambda 1t, e to the lambda 2t, 0, 0. Good. So if we go ahead and plug this in, we get phi of t equals m negative 0.781, 1.28, 1 times e to the lambda 1t, 0, 0, e to the lambda 2t. And then m inverse, which for a 2 by 2, so we'll put the factor out front. So you flip these two, so you're going to go 1, negative 0.781, and you change the sign on these. And you divide it by the determinant, which is the determinant of the original one. So that's negative 0.781 times 1 minus 1.28 times 1. And now it's just multiplying the matrices out, right? And I think that well, it's worth going through. Let's go through it. So the order doesn't matter, or sorry, the order does matter in terms of which matrix comes first, but the order that we decide to do the multiplication in terms of should we multiply these together first or these together first, that doesn't matter. We can choose whichever one we want. So let's do these first two together. So negative 0.781 times e to the lambda 1t plus 0. So negative 0.781 e to the lambda 1t plus 0. Okay, so that's that entry. The next one's going to be negative 0.781 times 0, 1.28 times e to the lambda 2, so 1.28 e to the lambda 2t. That's that one. Then we're going to get e to the lambda 1t, and we're going to get e to the lambda 2t. And we're still going to need to do this. 1.28 negative 1, negative 0.781. And then what is that? Negative 2.9 0.06 or something like that. And then we can do the next one, and I kind of don't want to do the next one because it's just gonna you're gonna pick up an e to the lambda 1t and an e to the lambda 2t in both of them, and it gets kind of messy, right? So we're gonna end up with. So I'll just do this. I'll just say we're gonna end up with something that looks like something e to the lambda 1t plus something e to the lambda 2t plus, and then the next entry is going to be something e to the lambda 1t plus something e to the lambda 2t. And this is going to be the same on each of these. E to the lambda 1t plus something e to the lambda 2t. And then we can just include that factor in there. So we've got this matrix. So let's just say we did that. I mean, it's just like another matrix multiplication. Good times, right? But notice you have to actually do this by hand because your calculator probably can't keep that symbolic e to the lambda in there, right? So you got to do this by hand. Kind of sucks, but it's the case. You can use Mathematica or MATLAB to do it, but you'd have to be able to do it on a test. Don't worry, I don't give you guys things on tests that you have to write pages of stuff to calculate. Okay, so great. You've got your phi, and now you know that your free response, which is what I asked for in the problem, free response is just x, I'll put sub free, sub fr of t is equal to phi of t times the initial conditions, which are given in the problem as being 2, -1. So that part's easy. That multiplication, it's like once you have phi, you pretty much have the free response. You just have to multiply the state transition matrix by a vector, and then you're done. If you wanted the total response, with including the forced response, if you had some input, you'd have to do some integration. But if you just want the free response, the state transition matrix is practically the whole solution. So, yeah. Any questions on that? I mean, I think the formula is pretty easy. We spent most of our time computing the eigenvalues and eigenvectors, right? And a little bit of time doing some calculation. I hate wasting our time with calculation in class. I trust that we all can multiply numbers together and stuff. So
if you were to give us a question like this on a test, would it include the first part, or? Yeah,
but it probably would be so you should be able to do eigenvalues and eigenvectors pretty quickly. Like that.
Set up to 3x3s?
Up to 3x3s, yeah. And then I probably wouldn't have you guys multiply through the whole thing. I might ask you guys what's the free response in the primed coordinates? That might be a good question because the state transition matrix in primed coordinates is just that, right? And that one's super easy. So I might say, what's the free response in primed coordinates? Computing the transition with these two matrices, that's where it gets kind of messy, right? Or I could just give it to you a problem that has a lot of zeros in these matrices, so that if you have a lot of zeros in these matrices, then the multiplication is pretty easy. So, or I could give you ones that have, instead of decimal results, I could give you ones that have nice, clean fractions and whole numbers. that are easy too. So I try to ease computation on tests, but I mean, be able to do all of these steps and in a reasonably quick fashion. I mean, I don't expect you to be able to do like, yeah. Cool. Learn how to use your calculator for doing things like, the eigenvalues and eigenvectors. Like, I think that is fine. I don't care if you guys use them. Just write on your page, calculator, result. But if you key it in wrong, you can't really give you a lot of partial credit if it's just wrong. So, yeah. Okay, any questions on this or any further questions, I guess? I have one more lecture on this chapter, and it's an example. Okay.